This is quiz 5 solutions for problem 1. We're given this is f of x. We are told to write it in the form a x minus h squared plus k. Then describe the shifts to x squared in order to get that. Then find the zeros of the function. And finally to graph it. So, all right, so we have to complete the square. And so I'm going to give myself a little bit of room here, putting the 1 over there. I'm going to factor out a 2. When I do that, that leaves me an x squared right here. And then to factor that out of there, that would be 4 over 2. Or I could say, oh, hey, that's nice. 4 over 2 is just 2. And so, okay, that's minus 2x right there. Haven't changed anything. I'm going to take a step here and say, let's just make sure that we haven't changed anything. The 2 comes back in and would give me 2x squared. The 2 comes back in. I have minus 2 times 2 would give me 4x. There's the plus 1. We haven't changed anything. Okay, so let's complete the square. We take half of that. Half of 2 is 1. And so I add 1 squared and I minus 1 squared. There we go. Still haven't changed anything. I'm just take a second again and say, yep, that comes out to 0. And I remember that all that other stuff didn't change it. So I'm still good. Now this happens to make a perfect square. And so I'm going to rewrite that as the perfect square, which should be x minus 1 quantity squared. This minus 1 squared is still there. Okay. I'm just going to double check and make sure that gives me that back. First, outer, inner, last. First gives me x squared. Outer and inner give me a minus 2x. Yep, the negative 1 times negative 1 gives me a positive 1 right there. Okay, so I haven't changed anything. I need that 1 right here. Don't forget that. Okay, this is easy. 1 squared is just 1. I'm not even going to think about that. Okay, so distributing the 2 back in, and I get 2 times x minus 1 squared. Minus the 2 comes in, gives me a 2 plus 1. Just double checking, like, yep, that right there is the same thing as that. All right, there's no difference there. Okay, so now we're just left with minus 2 plus 1 gives me a minus 1. So there's that guy right here. And there's my first answer. F of x is equal to that right there. Now, we're going to describe how that is x squared transformed into that. So the first thing that happens is you take x squared, and this is a shift right 1 unit. Okay. Then the next thing that happens is this gets multiplied by 2. So this is a vertical stretch by a factor of 2. Okay. Then the last thing that happens, so the first thing that happens to x is he gets subtracted 1, which is a shift right 1 unit. Then he gets multiplied by 2, so that's a vertical stretch by a factor of 2. Finally, we get a subtract 1. We're subtracting 1 from the output values. It's another way of looking at it. And we're saying, okay, so that should be a shift down. Shift down 1 unit. Okay, so there is the answer to part 2. Now let's go ahead and find zeros of this guy. Okay, so the zeros of a function are by definition when the outputs of the function are 0. So I'm going to say, when is f of x equal to 0? And now I'm just going to replace f of x with this guy. We have 2x minus 1 squared minus 1 equal to 0. I add 1 to both sides. Here brings the 1 over here. Divide both sides by 2. I get x minus 1 quantity squared equals, dividing by 2 gives me 1/2. Okay, let's take a square root. Take a square root here. When I take a square root, I get a plus or a minus. So I'm left on this side with x minus 1 On this side, I get a plus or minus the square root of, but I don't really like to write it like that. I think about that as the square root of 1 over the square root of 2. Square root of 1 is just 1, so I could simplify it a little bit by writing it like that. If you keep it like that, that's fine too. It's just that's a little bit more simplified. And you'll notice I don't bother rationalizing the denominator. If I wanted to, I could say 1 over the square root of 2 is equal to 1 over the square root of 2 times 1. But I could write 1 as anything over itself. So why don't I write it as the square root of 2 over the square root of 2? And so we could rewrite that as the square root of 2 times 1, which is just the square root of 2, over the square root of 2 times the square root of 2, which is just 2. And so that 1 over the square root of 2 is exactly the same thing as the square root of 2 over 2. If this were a problem in a textbook, that's probably how the final answer would be written. I don't care. I keep it like that. That's perfectly fine. If you did this, or if you did that, that's perfectly fine too. So finally, we want to get the x by itself. So I'm going to add 1 to both sides. That gives me x equals positive 1 plus or minus 1 over the square root of 2. So if you want to be really cool, you could write this in a solution set and say, okay, then x, the zeros of x are in this set. One is 1 minus the square root of 2. The other one is 1 plus 1 over the square root of 2. Like I said, 1 minus 1 over the square root of 2, and 1 plus 1 over the square root of 2. So those are the zeros of that function f. Finally, we need to graph this guy. One thing that's going to be, and I say in the graph to label all intersections. Every one of these polynomials is definitely going to go through the y-axis. Why is that? Well, something goes through the y-axis whenever the x value is 0, right? So we could just plug in when the x value is 0 and see if we get an output. If it's a polynomial, you're going to get an output. And so what do we get? Well, when x is 0, we get, oh, nice, a big fat 0. A big fat 0 plus 1. This is a really easy one to do. So this means that this is my y-intercept, right? Because if we're on the x-axis, you must be, I'm sorry, if you're on the y-axis, then your x value is 0. Conversely, if your x value is 0, you must be on the y-axis. So that lets me know that when x is 0, in other words, when I'm on the y-axis, my y value is 1. So, all right, we should have enough information to graph this guy. And we know this is just the original parabola x squared shifted right 1 unit, stretched vertically, and then shifted down. So I can imagine what that looks like. That's one way of thinking about how this guy's going to look. But then the question is, well, hold up. How far is it shifted down? Is it shifted down so far that it comes through like that? Is it only shifted down a little so that it comes through like that? Not sure, but that's where this is going to help us out a lot. We could say, well, I know that here when x is equal to 0, the output value is y. I mean, is y equals 1. And so we must have that type of picture right there. Okay, and so that's what I'm going to graph right there. All right, so we know it's an upward facing cup, so it does something like that right there. Okay, the vertex, well, we already said where it has to be, right? Because it's a shift right of 1 unit. Goes through there. 1, shift down 1 unit, and so that's where that vertex must be, right here. And that's labeled enough. I don't need to go in and call this point 1 minus 1. Like the information's right there. I could see that that's what we're talking about. You have the little tick mark right there with labeled with 1. You have a little tick mark right there labeled with a -1. If you went ahead and did that, that's cool. That's really cool. I appreciate that, but it's unnecessary. You could just leave it like that. So, okay, now the only thing that remains is these 2 places right here, right? And so that one has to be the one on the left. Another thing you'll notice is that these always split the vertex. That vertex value is 1. And so we're going to go plus the square root of 2 to end up over here at 1 plus 1 over the square root of 2. I meant to say 1 over the square root of 2. And then for this one, we're going to go minus that amount. This says go to 1 and then go back by 1 over the square root of 2. So you go to 1 right there. I'll just put it right here. 1 minus 1 over the square root of 2. Looks a little ugly, but if you drew exactly that, I would know what you're talking about. And if you want to be really high speed, you could put X's and Y's and arrows on this guy. And for like extra credit, if you want to label this as f of x equals to, I won't actually give you extra credit for this, but you know, I'm just saying it would be super cool if you did that too. But ultimately unnecessary. We got all the interesting points labeled. Okay, it agrees with this. And I think that's it for this one. Problem 2, same setup. We're finding the same 4 things. The function's the only thing that's changed. So we're going to complete the square to turn this function into a form that we could use. And so to complete the square, first thing I'm going to do is give myself some room, put my minus 63 over here. Now I'm going to factor out that 3, whatever that leading term is, the leading coefficient of the leading term, I'm going to factor him out. That leaves me an x squared plus, not going to use my brain, whatever that is, divided by that right there. Okay. 12 divided by 3 happens to be 4. Write it like that too. This is kind of nice when you go to check it. You could say, okay, the 3 jumps in and gives you that right there. Yep, the 3 jumps in and gives you 3 over 3 cancel and you're left with 12. Yep. Okay. Now I know I don't want to actually leave it like that. We could if we wanted to, but I know I'm about to add and subtract that thing squared, and then I'll be dealing with, well, half of that thing squared. It'll be 12 over 6, and then it's like, well, then you have 144 over 36. That's just terrible. So anytime you can, go ahead and let's reduce that guy. 12 divided by 3 is 4. But that's what went through my head, actually. What I saw was I'm dividing something out, I'm factoring something out. That means I'm taking this over whatever that thing that I'm factoring out is. I happen to know that 12 over 3 is 4, and so there we go. Oh, that's a nice even number. That's pretty sweet. Whoever wrote this test must have been thinking about me. They must have cared, because half of 4 is 2. That's an easy one to do. So I'm going to go plus half of that thing squared minus half of that thing squared. So that's plus 2 squared minus 2 squared. Check everything, make sure I haven't messed anything up. That is still 0. No problems there. The 3 comes in, gives me 3 squared. 3 comes in, 3 times 4 is 12x. That's perfectly fine. If that's 0, then we're just left with a minus 63. Good to go. Okay, so moving on. 3 stays put, and I know the whole reason I did this in the first place was to turn that whole thing into a perfect square. And it's got to be x. It's got to be whatever that is, and it's got to be squared, and then the sign has to match right there. Since that's a plus, this is a plus. Okay, minus 2 squared right there, minus 63. Let's check it. Okay, I'm sure that that step's fine, so let's just make sure that that goes back into there. So first, outer, inner, last. First gives me x squared, outer 2x, inner 2x, and so that together gives me a positive 4x. Yep. 2 squared is 2 squared. Okay, yeah, that looks good. I believe it. Okay, 2 squared is 4. Okay, there's 4. So let's put this back in. The 3 comes back in and gives me 3 times x plus 2 quantity squared minus 3 times 4 is 12. Okay, I could drop the parentheses because I distributed in my 3. Now I minus the 63. Minus minus is like a negative. You add them together, and so 3 and 2 make 5, 6 and 1 make 7, so that should be 75. It should be minus 75. Plus 2 squared minus 75. All right, and that looks like we're done. So there's the answer to part 1. F of x is equal to that. Now let's figure out what kind of, how this is the graph of x squared shifted. So I'm going to start all the way on the inside with x. First thing that happens to x is he gets added 2. So that should shift left by 2 units. So this is x squared shifted left 2 units. Then he's stretched, because that's a positive number bigger than 1. So it would be a stretch up and down, a vertical stretch by a factor of 3. by factor of 3. There we go. Then what's the last thing that happens? I guess he gets a minus 75. So that should bring everybody down 75 units. So we'll call that a shift down 75 units. Okay, so that's part 2. All right, now let's find the zeros of this guy. Zeros of f, by definition, are the x values that give you an output of 0. So we're saying, okay, we have f of x equal to 0. And so let's rewrite f of x like this. We have 3x plus 2 squared minus 75 equals 0. When are the outputs equal to 0? Well, we have a minus 75, so let's add 75 to both sides. It's me a 75. 3x plus 2 squared. Just, the reason, and I don't think I said this last time, but the reason I'm doing that is because, remember, it's just like we're trying to get x by himself. And if you're confused which one to do first, just think, well, what's the first thing that happens to x? Well, that happens. He gets added 2. Then he gets squared. Then he gets multiplied by 3. Then he gets minus 75. And so we've put our socks on, put our shoes on, then we put on our overboots. So we have to take off the overboots first. That's what I just did. Then we're going to take off our shoes. Then we're going to take off and so on, right? We're doing it in the reverse order that things happen to x. So, okay, so even if we're just starting right here, we could say, okay, what's the first thing that happens to x? Well, plus 2, okay, then squared, yep, then multiply by 3. Okay, so that's the last thing that happens. I need to get rid of that. Opposite of multiply by 3 is divide by 3. Divide both sides by 3. 75 divided by 3. Does that work? I have a hard time with that. Oh, wait a minute. 75 cents, right? That's 3/4. Oh, 3 and 25. Yeah, okay, yes. So x plus 2 squared. Dividing both sides by 3 gets rid of that 3. 75 divided by 3 should be 25. Yeah, nice. Oh, and it's also a perfect square. This will be nice. Okay, so this looks good. Now we have something squared. Let's unsquare it by taking a square root. When I take a square root, I get a positive and a negative answer. And so what's left here is x plus 2 plus or minus the square root of 25. Like I said, that's a perfect square. This should be easy. So that should just be plus and minus 5. Okay. Need to get the x by itself. So I'm going to subtract 2 from both sides. And I get x minus 2 on this side plus or minus 5, which gives me 2 bits here. Either minus 2 minus 5 or minus 2 plus 5. Minus 2 minus 5 is minus 7. Minus 2 plus 5 is positive 3. And so we'll be slick here and say that x is either negative 7 or 3. There we go. Those are my zeros. That also tells me where this thing goes through the x-axis. So, all right, the last thing to do is graph it. One thing that will help me graph it is to find out what that y-intercept is. The y-intercept occurs when x is equal to 0. So we plug in a 0 and get 0 plus 0 minus 63. And so f of 0 equals negative 63. Okay, so let's put this all together. I know it's a shift left 2 units and down 75 units. So I'm going to be somewhere down here. I also know it's going through at minus 7 and 3. And so I'm just that's why I chose to draw it like that. We know that the y-intercept is minus 63. We also know that the vertex, it was over at minus 2, because we shifted left 2 units, and then down 75 units. So that should be right here at minus 75. I'm sorry, I didn't label that. I just said that where it goes through the y-axis is at minus 63. Okay, negative 7 is on that side. So I'm going to go over to about here. call it -7. We're going to go over here to, we're going to call that +3 right there. And remember how, again, something to notice, remember how this was done, right? How I got this. We said that x was equal to -2 plus or -5. So in other words, you go to -2, that's where your vertex is, right? And then you go +5, -5. It's halfway between those 2 points. So one of them goes up this way. The other one goes up this way. And yeah, that is what the parabola x squared, if you shifted it over 2, stretched it by a factor of 3, and then brought it down a total of 75 units right there. That has everything we want. Everywhere that goes through one of the axes is labeled. We also have the vertex labeled. It is at -2, -75 right there. Problem 3, write that in the form that we want by completing the square. So I'm going to complete the square, give myself some room. -6 moves over here. I know I'm going to factor out a -5. You got to be careful when there's a sign on that guy. That -5 is going to come out. It leaves me x squared. Now, factor out that we would have a 2 over -5 right there, right? Or you could also think about it as factoring out a negative flips the sign right there. And so, yeah, that's what we should have, 2 over 5x like that. Parentheses up there. And now let's just check it, make sure we haven't changed anything. That 6/5 stays there, that's fine. -5 comes back in, hits that guy, we're good, still -5x squared. -5 comes in, the sign's going to change. Negative times a negative is a positive. The 5 will kill the 5. The only thing that'll be left will be a +2 in the numerator, plus 2x, that looks good, okay. Now we're going to take 1/2 of that. Another way of thinking about that is you throw a 2 in the denominator. You could have it like that. Now there's 2 ways of thinking about this. You could say, oh, that's 2/10. Another way you could say it if you double the denominator, if that's how you have it in your head, you get half of something, just double the denominator. But I know that I'm about to square this thing, and I don't want to work with 4 1/100ths. I would like to make this as simple as possible. If you think about it as throw a 2 in the denominator, and you happen to have a 2 in the numerator, you could just say, oh, 2's cancel, and that's the same thing as 1/5. And if you're wicked smart, you could say, wait a minute, 2/10 is 1/5. But I would miss that. That's just, that would go right by me because I wouldn't be thinking about it. And so the way I like to think about it is, okay, we have it already factored, the 2's cancel, we have 1/5. Okay, so 1/5 is half of that. I'm going to add it and subtract it squared. So we take it like that. That's what I'm going to do. It's 1/5. So there goes the 1/5. Just like that. Okay, let's double check and make sure I haven't changed the overall picture. Something minus itself is 0. That's not even there. And I've already checked that when I distribute that guy in, that's fine. And so this is exactly equal to that thing right there. We have not changed anything. But now we have the benefit of having a perfect square. And so we'll deal with that in just a second. I'm just going to copy down the stuff that's not changing. So this thing is a perfect square by design. That's why we wrote it the way we did. And the first thing must be x. The last thing has to be 1/5. And the sign has to be negative. So let's check it. First, outer, inner, last. First, give me x squared. Outer would be minus 1/5 x. The inner would be another minus 1/5 x. And yep, what do you know? That's minus 2/5 x. And so that's what we have right there. Good. The last would be that times itself would give me a positive 1/5 squared. Okay, so that looks good. I think we're good. Moving on. Now, a couple of ways we could do this. I mean, we could go ahead and call this minus 1/25. Or we can think about it as 1/5 squared. In any case, what's going to happen? Actually, let's go ahead and write it that way. We'll just do this. Take one more step so that we don't mess anything up. Okay, I'm going to think about this as 1/5 squared, like that. Okay, minus 6/5 finally. Okay, that's still bad. Okay, I haven't changed anything. We're still good. Now, oh, this is where it's tricky. We have a -5. That -5 has to come back in. Okay, so we have a -5 times x minus 1/5 quantity squared. A minus times a minus is a positive. Okay, the 5 goes into the numerator. There are 2 5s in the denominator. Oh, that's nice. That's kind of why I kept it like that, right? 1 5 in the top, 2 5s in the bottom. Well, one of those 5s is gone, and we're left with just 1/5 left over. Alternately, had you written it like that, had you just squared that guy out, right? You would have multiplied the 5 through, and you should know that 5/25 is the same thing as 1/5. Any way you like to do it, you're gonna end up with 1/5. Okay, and so that's that. Finally, that those parentheses can go away because we have distributed this 5 into both of those guys there. So that parentheses is gone, and I could say minus 6/5. Oh, that's nice. 1/5 minus 6/5 is minus 5/5. Minus 5/5 is just -1. So altogether, we have -5 times x minus 1/5 squared. All of that we just said came out to -1. Therefore, f of x, because we're sure we have not changed it at all. We have not done anything. We just wrote it differently. F of x is equal to that right there. Okay, part 1 is done. Now let's figure out what this does to the graph of x squared. We could say, well, you have something squared and it's just x squared, but it's just been shifted. And it looks like it has been shifted, since we're subtracting off 1/5, that means we are shifting it to the right 1/5. So first thing is shift right 1/5 of a unit. Okay, so working our way out. Now, -5, we could think about this a couple ways, right? I'm going to think about the stretch first. Thinking about this as, well, this is the same thing as first multiply by 5, then make it negative, or then multiply by -1. So then that would be a vertical stretch by a factor of 5. So vertical stretch by factor of 5. Then we'll make it negative. So then what does that do? Well, that takes all the positive points and turns them into negative points. It takes all the negative points and turns them into positive points. So it is a rotation about the x-axis. Or a flip, I don't care what you want to call it. Then what do? Well, now we shift it down 1 unit. Okay, so then it is another shift down 1 unit. And that is the answer for part 2. Now, real quick, let's just think about what that's going to look like. So this is not the last part here. I'm just kind of thinking what happens, okay? If we had our original parabola here, that's just regular old x squared. We took it and it says we shifted it right 1/5 of a unit. Okay, so it moves over here to 1/5 and it looks like this. All right. Then we stretch it upwards. Okay, so it stretches up like this. Then it flips down, right? It's a rotation about the x-axis. Finally, we shift down 1 unit. So this last thing should look something like this. Getting all this mess out of the way, our final picture should look like this. We have 1/5 here, -1 here, and it should be going down like this. It does not cross the x-axis. All right, this is the x-axis. So as soon as I know this, I should be anticipating my zeros should be imaginary, right? The only way you're going to get pure, real zeros is if it actually goes through the x-axis. When it doesn't, we should anticipate, we should anticipate imaginary roots, or imaginary zeros. So let's see what happens. So just keeping that in mind here, that is what we should see. Okay. So let's find the zeros, right? We want to solve f of x equals 0. Find out where that bad boy is equal to 0. Well, where's that bad boy? That is minus 5x minus 1/5. Quantity squared minus 1 equals 0. Add 1 to both sides. Okay, there's 1 over there. Minus 5x minus 1/5 squared. Ow, okay. And this is where that whole complex number thing is going to come into play, because I see, okay, I have a -5 over here. So I got to divide both sides by -5. When I divide this by -5, it just comes out to be this. Just gets that guy by himself. When I divide this by -5, I get 1 over -5. We can also think about that as -1 over 5. And now I'm going to take a square root, and that is what I was expecting, right? I'm expecting to get imaginary units because this thing does not cross the x-axis. And so I'm feeling pretty good about this. So let's do this. Take the square root of both sides. Take the square root. When I do that, I get a positive and a negative answer. Don't want to forget that. This thing goes away. And now I have what? Well, let's think about this. The square root of a negative number is the same thing as I times the square root of that thing, but made positive, right? So another way of thinking about that is we could pull out the negative by calling it an I. So we still have a plus or minus of I, and now we just have the root, right? And this was kind of like earlier when we had the square root of 1/2. I like to think about it as, well, that's like the square root of 1 over the square root of 5. Square root of 1 is just 1. So I'm just going to write that as 1 over the square root of 5. And I'm not going to bother to rationalize the denominator. That's perfectly fine right there. So, okay, let's see. Almost done. I just need to get the x by itself, x minus something, get rid of it by adding it to both sides. So I should have x equals plus 1/5 plus or minus I times 1 over root 5. And I want to be slick, so I'm going to write that, oops, x is in this solution set. Let's do the minus first. So 1/5 minus that'll be 1/5 minus I times 1 over root 5. The other one is going to be the plus. So 1/5 plus I, 1 over root 5. There you go. Those are the zeros of that function. Now, finally, let's graph this guy. Pretty much already done it, right? We know what it should look like. And had we not done that analysis, we get to this point and go, oh, hey, look at this. I have imaginary zeros. That means this thing does not go through the x-axis. And so there's another way we could check ourselves as we go along. And let's figure this out. So just like what we did before, we're going to say, okay, this thing got shifted over to positive 1/5, and it got shifted down 1 unit. So the vertex should be here at -1. We also know it's a downward facing parabola, but even if we didn't at this point, we could say, well, hold up. Let's find out where it goes through that y-axis. That happens whenever x is equal to 0. So I plug in a 0 and I get a 0 plus a 0, right? Because we 0 squared just gives me a big 0 right there. 0 gives me a big 0 minus 6 over 5. And so the y-intercept is -6/5. -6/5 is less than 1. right? Yeah, because that would be minus 5/5. So minus 6/5 would be further down. It would be right here at minus 6/5. And that kind of makes sense. If I know that's my vertex and it goes through that point, well, it has to be going down like that. We already knew that, but if we didn't, we'd be at this point. We'd say, well, it has to look like this. And we'd be done. We have the vertex labeled. We have the y-intercept labeled, and we could see that it does not go through the x-axis, which agrees with our picture. So we are done. Problem 3, we're going to complete the square first. So give myself a little bit of room, write the plus 1/2 over here. Now I'm factoring that number out. I don't need to use my brain at the beginning. I'm just going to write that thing out there and the x squared like that. That's easy enough. Now, yikes. Well, what am I doing? Technically, what I'm doing is I'm taking whatever that number is and dividing that number by it. I'm taking 3, and it happens to be minus out here, and I'm dividing it by -1/2, which is 3 times the reciprocal, 2/1. And I already know, well, I'm factoring out a negative, so this thing's going to be positive, right? And if I were doing it this way, I would say, oh, we have a negative. That's the same thing as a positive, right? And so we end up with 6 right there. One way of doing it. Another way of doing it is saying, well, hold up, if factoring out a fraction, you could just multiply by its reciprocal, which is what I did right there at the very beginning. You could just think about that as saying, well, factoring out a fraction, that's the same as just multiplying by its reciprocal. And what do you know? You end up with that. In either case, what I'm going to do is I'm just going to write it down, kind of take it on faith right now. That works. And now I'm going to check it. I always want to check this. And so the -1/2 comes in and gives me -1/2 x squared. Good. -1/2 comes in. And what my brain is doing right now is I'm seeing the -1/2 jump over the plus like this. And there's that 6 right there. And I see, yeah, okay, the minus is going to make that whole thing minus. 1 times 6 is 6 divided by 2. Oh, that's the same thing as 6 divided by 2. 6 divided by 2, that would be a -3. And so, yeah, that comes in, the 6 over the 2 give me a 3, and it's negative, making the positive a negative. Yep, okay, that checks. That works. Okay. So we would end up with that right there. The +1/2 comes along. Okay, so we haven't changed anything. We wrote it in a different way, but we really have not changed that. Now, okay. Now I need to add and subtract something squared in order to turn this thing into a perfect square. The only thing that works is going to be half of that number. Half of 6 is 3. So I'm going to add 3 squared and subtract 3 squared. So I don't want to change it. I'm going to make sure that that worked, right? Those guys, that minus itself is gone. And well, then what I'm left with was that. I already checked that. I already know that that equals the original thing. So I haven't changed it. We're still good. This is still all equal. So -1/2. The whole reason I did that was to turn this thing into a perfect square, which it is. Now I just want to write it that way. So I'm going to say, okay, this thing is x plus or minus something squared. And well, it has to be plus because that's the only way you could get a plus there. Okay, so that works. And the last thing ends up getting squared. Well, that has to be the last thing, right? Okay, let's double check that. First, outer, inner, last. First gives me x squared. Yep. Outer is 3x, inner is 3x. So for a total of 6 x's, yep. 3 and 3 gives me 3 squared. There we go. Okay, so we have not changed anything. This is 3 squared right there. Okay, why don't I, oh, not quite. Now we haven't changed anything. Okay, now we're ready to go. So I'm certain that this is the same thing as this, and I'm certain that this is the same thing as this and this, and so we have not changed anything. Everything looks good. Now, why don't I just go ahead and rewrite 3 squared as 9? Save myself a little bit of space here. Okay, so that works. -9. Remember, that's always going to be a minus. always going to be a minus because the plus thing always, always, always goes with that. And I don't care if that's a positive or a negative. Like when you square it, it will always come out to be plus. And so your minus is always coming along. Okay. So let's distribute this guy in so that we could drop the parentheses. We distribute the -1/2 in and it hits this guy, giving us that. Now, okay, a minus times a minus is a positive. A 9 times a half is 9/2. So 9/2. Okay, I think we have distributed this in so we could drop these parentheses that have gone. Now all that's left is I add 1/2. Okay, nice. 9 halves plus 1/2 is 10 halves, but 10 halves is 5. So I'm just going to rewrite that whole thing right there as 5 minus 1/2 x plus 3 squared. All of that should just be plus 5. All right. So there's my first answer. I've completed the square to rewrite the original function f in the form a x plus or minus h squared plus or minus k. Got it. Now, let's describe how that thing is the graph of x squared shifted. Well, first thing that happens is the +3. So that should shift it to the left 3 units. So this is a shift left 3 units. Okay, then what happens? Well, we get multiplied by a half. I'm going to think about that, the negative later. First thing is when you multiply by a half, you're taking half of that height, right? If you're up at 7, you take 7, multiply by half, brings it down to 7/2. So you're up at 10, multiply by half, well, it brings you down to 5. So multiplying by 1/2 is a vertical compression. So this is a vertical compression by a factor of, I don't care how you say this, I'll know what you mean. You could say by a factor of 2 because it's, you know, it's like 2 is a half, but it's, yeah. And so, yeah, by a factor of 2, or you could say compression, you know, to 1/2 of the original height. If you said by a factor of 2, I mean, by a factor of 1/2, I know exactly what you mean. That's fine. You know what you mean. I know what you mean. I'm not going to nitpick about that. So, okay. So, okay, we've shifted left. We've compressed the graph. Now, what that negative means, it's going to flip the graph. So we call that a rotation. Or no, have I been calling it a rotation? It's a reflection about the x-axis. So I said that earlier in the video. Sorry about that. It's a reflection about the x-axis. Could think about it as a rotation if you're talking about 3-dimensional space, but we're not going to think about that. Sorry, that was my bad. I shouldn't have said that. So, okay, reflection about the x-axis. Finally, this guy gets shifted. And since we're talking about adding to the outputs, that is a shift up by 5 units. So that is a shift up 5 units. Okay, there's our answer for part 2. And real quick, I could just imagine what that looks like. It's shifted left, compressed, reflected, and shifted up. So I could imagine, okay, taking this thing, shifted it over, reflected it, and then shifted it up. It should look something like that. So we are expecting real zeros here because it does go through, it should go through the x-axis somewhere. So that's in the back of my mind as I continue along. Okay, so now let's find the zeros for real. We have f of x equals 0. We want to find what values of x make this thing equal to 0. Well, 1/2 x plus 3 squared plus 5 equals 0. The last thing that happens is the +5. So let's minus 5 from both sides. And at this point, you might be going, oh no, we're supposed to have real zeros, but if I take the square root of that, I'm going to have an imaginary number. That guy's negative, right? And we need to get rid of that negative. So a few ways of doing this. We could divide both sides by -1/2, or we could just multiply everybody through by -2, right? Dividing by a negative is the same thing as dividing by a fraction is the same thing as multiplying by its reciprocal. So let's just do it that way. I need to kill that 2. So let's kill the 2 by multiplying by 2. Well, let's do this all in one fell swoop. We want to kill the -2. So let's kill the minus that way. So I'm going to multiply both sides by -2. Why did I do that? Well, that -2 kills that -2, kills the negative. Everybody's gone, which was the goal. We're trying to get this x by itself. So we're clearing out all the stuff in front of it. -5, -2 gives me a +10. And now I feel a lot better. I know that this thing should have real zeros, and I do indeed see that we're going to take the square root of a positive number, so we're good to go. Okay, so let's do that. Take the square root of both sides. Take a square root, you get a positive and a negative answer. So x plus 3 is plus or minus square root 10. Can't reduce square root 10. I'm not making you reduce stuff anyway, but if it were like square root of 9, we'd do it. If it were square root of 8, we could reduce that, but 10 you can't reduce. It's 2 times 5. It's done. So we're close to done. X plus 3, we need to get rid of that by minusing 3 from both sides. Okay, so that gives me 2 answers. Whatever -3 minus root 10 is, and whatever -3 plus root 10 is. And so I'm going to write that as a solution set and say, okay, x is -3 minus root 10 and -3 plus root 10. There we go. Those should be the zeros of that guy right there. All right. Finally, we're going to graph this. In order to graph it, it will be in our best interest to find where it crosses that y-axis. Where does it cross the y-axis? Well, whenever you're on the y-axis, your x value is always equal to 0. And we could, I didn't say this earlier, we could, if you want, plug it into there and do a bunch of stuff and find what the output is, but you would find that it's always going to be that, what we get in this case. Why? Well, how did we get this? We said at the very beginning, we were completing the square. Every step along the way that we took, we said, oh, this is the same thing. We just wrote it a little bit differently. So if you want, go ahead and plug 0 into there, and you'll see that when you do all of this, you'll get that as well. They are exactly the same. They just look different. So long story short, that goes through the y-axis at 1/2. So we have enough info to do this. That's kind of nice to know too, because, well, as I can see, this is negative. -3 is negative. Minus something goes further that way. But now we have -3 plus root 10. Is that a positive number or a negative number? I'm not too sure. I think it's a positive number, but I'm not 100% sure. So this is going to help us with that, right? Let's get the general idea of where this thing should be. We're going to shift left. We're going to compress and then reflect and then shift up. So the interesting stuff's going to be happening somewhere up here. Okay, shift left by 3 units. And so we're here at -3. Finally, we're going to be shifting up to +5. So that's where the vertex ends. There. Okay, so that's my vertex. Now I know this thing goes down because we reflected around the x-axis. So this thing has to come down. The only question, remember, was like, we know this guy's negative. So when it comes over here, it's got to be the -3 minus root 10. But is the -3 plus root 10 on this side of the y-axis or on that side? Well, that's where that's going to help us right there. You could say, I know that it goes through the y-axis at 1/2, because when I plug in a 0, I get out a 1/2. Oh, okay. So if it's going from there and it's a little downward cup thing that comes down like that, well, it's got to go through here. Down like that. And so I could surmise that this guy is a positive. I'm going to call it -3 plus square root 10. The other one, it's symmetric. I'm going to try to draw that about equal distances, because remember what the root said. It said go to -3. Yep. And then go that way by root 10. Okay. And so you end up at -3 minus root 10. The other one says, well, you go to -3 and then go that way by root 10. And where do you end up? Well, -3 plus root 10 right there. So those things are the same distance away. I'm not going to be pulling out a measuring tape or anything. It just, that's a nice picture right there. And even if it was very wonky, it wouldn't matter, because all I've asked for is qualitatively accurate. Okay, so there's the graph. And I think we've answered everything we need for problem 4. Problem 5. Now you might notice right off the bat that you could actually factor this thing. It ain't too bad, actually. Like, check this out. You could say, well, I need an x and an x. If this thing's going to factor, we have to have an x times an x to give me that. First, outer, inner, last. Well, the last is 7. There's only one way to get 7. So long as we're talking about multiplying integers here, it's got to be 1 and 7. It's got to be, one's got to be positive, one's got to be negative. And oh, lo and behold, adding and subtracting 1 and 7 together, I can get a -6 if I make this guy negative and make that guy positive. Let's just check it. First, outer, inner, last. First gives me x squared. Outer -7, inner +1. -7 plus 1 is -6x. Okay. -7 and +1 multiply to give me a -7. So I already know the roots of this guy. I already know the zeros of this function, right? I know that in the end here, I should have one of my zeros will be x equals -1. The other one's going to be +7. This isn't necessary, and this isn't the way I asked you to do it. It's just that I can confirm, because I know I'm going to eventually do, do a bunch of stuff to this, make it look a lot different, and do a completely different way of solving this. It'll be nice to say, well, hold up. I know that this thing factors and that these are the roots of it. If you wanted, you even could go ahead and plug in each one of these, a -1 squared, okay, and a -1, plug it in and see, yeah, okay, I do get 0 as an output. Plug in a 7, square it, then a 7, and do all that, and you see, yep, I do get 0 as an output. And that'll be nice, because then when we get to our final answers and stuff, we could feel a little bit safer about it, especially since we're going to be completing the square. This thing's going to look crazy in a minute, and it'll be nice to do that. So if we can take advantage of another way of checking our work as we go along, it's sometimes worth it to do. Sometimes you don't have time, and I understand that, especially with a quiz. But in general, it's nice to be able to verify your work in more than one way. So I'm going to go ahead and keep this there, that we obtained by factoring that guy and finding our zeros the old-fashioned way. So, okay, moving on with the problem. Let's complete the square. Oh, this is nice. We have nothing to factor out. So I'm just going to give myself a little bit of room and say, okay, I really don't even need the parentheses here, but that's just how I do it. We're going to say, well, this guy is already in the form that we're looking for. Now I just need to take half of that. Half of 6 is 3. So I'm going to +3 squared minus 3 squared. And double check that I haven't changed anything. That goes down to 0. And oh yeah, obviously we still have the same thing. Nice. Okay. All right. The whole reason I did that was to give me a perfect square. And so that's what it's going to look like. I like doing all the stuff that I know is not changing first, so I don't forget about it. Okay, that thing is going to come down to an x right here and a 3 right here. The sign in between them's got to be a minus. Now let's double check it. First, outer, inner, last. X squared, yes. Outer gives me -3x. Inner gives me -3x for a total of -6x. Good. -3 times -3 is a +3 squared. Yes, okay. So that has not changed at all. Oh boy, look at that. I don't even need the parentheses, do I? Because we don't need to distribute anything back in. So nice. Okay, don't need them. Let's drop them. I guess the only thing left is to actually square out the 3. So minus, that's always going to be minus whatever 3 square is. I guess that's 9 minus 7. Minus 9 and minus 7 should be minus 16. Okay, so x minus 3 quantity squared minus 16. And I believe we're done. That is the form that we're looking for. So there's my first answer. Rewritten it in the form we want by completing the square. Now let's describe how that is the graph of x squared shifted and stretched and transformed. And so the first thing that happens is a shift. It's a minus 3, so that means it's a shift to the right by 3 units. There's no stretching or compression, right? There's nothing out here to stretch or compress, so we don't need to worry about it. Finally, it's just a shift down because we're subtracting 16 from the output, and so that goes in that direction. So it's going to be a shift down 16 units. I already know what this thing looks like, right? It's just the original cup shifted over to the right and down 16. Okay, so I am expecting zeros. And this confirmed, like, yeah, I should have real valued zeros. So that's nice. So let's verify that what we got by factoring is actually the same thing we would get if we took this guy and set it equal to 0. So we're going to do that. Okay, so when does f of x equal 0? In other words, for what x values does that thing equal 0? Minus 3x 16. How about I add 16 to both sides? Okay. Now take square root of both sides. When I do that, I get a positive and a negative answer. I get x minus 3 equals plus or minus the square root of 16, I believe is 4. That should work. Now, to get x by itself, I'll just add 3 to both sides. So I end up with plus 3 plus or minus 4. Okay. 3 plus 4 is 7. Yep, that's what we got. 3 minus 4 is minus 1. Yep, that's what we got. Okay, that's nice. We verified that we can do this a couple of different ways. And now I feel that much better about my answer, right? So, okay, those are my zeros of this polynomial. All right, so let's get this out of the way. We're going to draw this guy. In order to draw it, it will be nice to know where this thing goes through the y-axis. It goes through the y-axis wherever x is equal to 0. So we get 0 minus 6 times 0 minus 7. So when x is equal to 0, y is equal to 7. And so he's going to be down at negative 7 on this. Okay, ooh, we're shifting right. Give myself some more room over there. All right. Okay, so drew it like this because I knew I'm about to shift right 3 units. And so I'm going to go ahead and write that there. And then I shift down 16 units. That gives me my new vertex, right? We just took the original x squared, grabbed it by the vertex, moved it over 3 units, down 16 units, no stretching or anything like that. And so this guy goes, and now I could verify, yeah, it does go through at negative 7, right? I don't need to worry about, oh, does this thing stretch way up like that or whatever. I could see, yes, negative 7 is, say, right here. I don't care where you put it. As long as it's between negative 16 and 0, it'll look great. There's -7 right there. And so it must be the case that this guy comes out over here. This guy comes out over here. I've tried to draw that relatively nice, but it doesn't really matter as long as this thing ends up on that side and this thing ends up on this side of 3. So, okay, it goes through, we know, at -1 and +7. What we're going to be talking about soon is the geometry of this. And if you haven't noticed this already, and I mentioned this like either last time or the time before, right? Your vertex, it's always, the way we even write it right here is 3. So it basically says that the roots, how do you find the roots? Well, you go to 3 and then you go +4. So you go over 4 units. And then you go back, right? The 3 plus or minus means 3 plus 4 brings us 4 units that way. -4 brings us 4 units that way. That's kind of what I was talking about that symmetry. That guy, that vertex should always be halfway between those 2 points. But again, as you're graphing, I don't really care. It's not one of the things I'm grading for right now. So that should be it. We have the vertex labeled at 3 -16. We see where it goes through each one of those points. They're all, or each one of the axes, all the points are labeled. And so we are done. Problem 6, I gave you a graph and said, that is the graph of f of x. And I have 6 points on there labeled. And I said, I want you to graph G. And I told you that G is equal to this guy right here. And so what this tells me is that I can take the graph of f and transform it in different ways in order to obtain the graph of G. In other words, it says that the graph of G is f, but the input has been shifted. And then we multiply the output, and then we shift the output. And so that's how we're going to deal with this. And I like to do it one step at a time. And the order I'm going to do it is it's kind of the same thing we've been talking about here, like when we're solving equations like this. What I've been doing is saying, well, the first thing that happens to x is this right here. Then he's getting squared, yes. And then he's getting multiplied. Then he's getting that added. And so that's the last thing that happens. And I was using that in order to find out the reverse way of doing it, right? But that's not what we're doing now. We're not trying to solve for x here, but we're still going to think about that order. Still, this function here says that you do things in a certain order, right? So if you think about it, I said, well, what is, say, g of 5? What would I do? I would say, well, I'm not too sure actually, but I know what this means. This means that if you take an input and say 5 and plug it in, what would you do? Well, at first I would just say, well, I have no idea, but I know what this kind of function notation means. It says, like, if you put a 7 here, you put a 7 there. You put a 5 there, you put a 5 right there. And so since I put a 5 here, I'm just going to replace it right here. Okay. And I'm going to say, okay, well, that's what you would do. Now, what would you do? Well, not too sure, but if I were to do this, if I actually had a function, if I knew that, say, f of x was equal to, oh, I don't know, like the square root of x or something, right? Then what I could do is say, well, hold up. I could actually do this first, right? I would say, what is 5 minus a half? And I would get that new number, right? And I would say, and this is a bad example. I shouldn't have used 5 1/2, especially with the square root there. But this is the idea, right? So maybe if this were 2 instead, say 2x, then I would say, okay, well, all this says 5 minus a half. 5 minus a half, that's 10 halves minus a half. Okay, so that's 9 halves. And so I could say, aha, well, I figured out that first. And so that's the same thing as f of 9 halves. But now that I know what the input to f is, Now I'll go and evaluate f, and I'll plug it in and say, well, what is f of 9/2? Well, that's 2 times 9/2. I guess that's just 9. Okay, because the 2's cancel. Yeah, I just get a 9. Then I could say, aha, okay, well, this thing was equal, sorry, I didn't write all that out. That's equal to all that. And so I do all of that, figure out, oh, that's a 9. Let's just think of it. And let's think about the order in which we're doing this. Now we're saying, okay, that is this and that. Now, what would you do? If I just told you, hey, compute that, what would you do? You'd say, well, -3 times 9 plus 1. Well, I guess we got to do the multiplication first. So you'd say, okay, I guess I will then multiply that and say -3 times 9 is -18 plus 1. And finally, the last thing we do is going to be adding 1. And so that's -17, I guess. Right? And that's how you would find something like this. Well, it's a similar idea going on here. It's like, although we don't have an explicit function here, if we wanted to, we could try to play around with that, but that's not really the idea. All we're trying to get at is the order. And let's look at that order again. And if you've been paying attention for the last couple of weeks, this is probably a bit too much for you, or not too much, but this is you've heard this before, right? And you're like, just get on with it. But I really want to beat this point home, is that in order to solve this thing, if I know what input I'm getting, the first thing I would have to do is mess with that input, right? Since that input is being messed with, I would first have to do that. And then what would I do? Well, I'd have to evaluate whatever it is. And yeah, but we have that information here. The next thing you would have to do is then multiply it, right? And then finally, the last thing you do would be add right there. So that's the order we're going to go to figure all this stuff out. It's the same thing you would do if you actually had an input and you plugged it into this function. This is what you would do. And so that's also has to be the order we use to graph this guy. So, okay, my first step is going to be to figure out what does this do to my function. Well, I'm subtracting off of an input. So what I'm going to do, this is the graph of f. Let's graph f of x minus a half. So if that's f of x, we just subtract from the input. That has the effect of shifting the original graph 1/2 of a unit to the right. So that's not too bad, actually, because they're all halves. And so, okay, this is an easy one. Let's just start with that one right there. That minus 1/2 needs to come over to the right 1/2, and he's going to end up right here. None of the heights are changing, right? We're just dragging this entire picture over. And so this thing that was up here at 1 and 0 has now been moved over 1/2 of a unit this way. We're still up here at 1, but now we're over here at 1/2. So that's that next point. This point that was at 2 3/2, he comes over 1 more half, right? So 3/2 plus 1 more half would be 4/2, or 2. That would be an even easier way of saying it. So he was up at 2, and then he got shifted over from 3/2, 1/2 of a unit over to put him at 4/2, or we'll just call it 2. That's where he ends up. Note, I am not trying to do any of this with the correct lengths at all. That does not matter here, right? Like you said, well, if that's 2, and but that looks more like 1. It doesn't matter. We're trying to do this just qualitatively. 5/2 gets shifted over 1/2 of a unit. So from 3/2, 4/2, 5/2, I guess he would come over to 6/2. But 6/2 is just 3. And so put the 3 right there. And it's going through. It has not moved up or down. It's just come right here. I'm going to put the 3 right there. I'm going to label that as 3 because I know what this thing looks like, right? This came up to there and came back down. So this thing comes up to there and comes back down. Just like that. Okay. Now how about these other points? Well, we had one at 5/2 and -3. And if he comes back over one more, let's just think about this. We have 5/2 with -6/2, -4/2, -3/2. Right? If you're counting by halves, that's what we'd have. And well, if you're moving over by one more half, you'd be over here at -4/2. So this point that was there moved over to -4/2. Still at -3, but now we're at -4/2. But -4/2 is just 2, right? So we're just going to call that -2. Okay, the last point, the one at -7/2 came back over by 1. Or I'm sorry, came over by 1/2. So shifting to the right would take me to -6/2. -6/2 is just -3. So that's that guy. Okay, so just took the original thing, shifted it over. So that means that this comes up like this and down to here and then back up. Then this comes up to here, back, down, and then up. Okay, so that's the graph of f of x minus 1/2. All right, let's see. Now, the next thing that happens is this guy gets multiplied by 3, or multiplied by -3, but I like to think about that in 2 steps. So I'm going to say, let's just do the 3 first. So if I took this picture right here and multiplied the outputs of it, right? Because that's what I'm doing. I multiply f. F represents the height. And so if I then take that and multiply it by 3, it's going to stretch everybody away from the x-axis. The thing that says my output is 1 will then get multiplied by 3. It'll get shot up to 3. The thing that says my output is 2, my height is 2, will then get multiplied 3. It should go up to 6. And so I'll just draw that. And you know what? I don't even really need to actually stretch this. The picture's gonna be pretty much the same thing. It's still gonna come up. It's still gonna come down. The only difference is where these things actually go. 1/2 has not changed. I didn't label the 0, but it goes through 0, 0. Okay, so when we're at 1/2 and up at 1, now we're up 1/2, and then when I multiply it by 3, that's what I'm graphing right now, 3f of x. Okay. I just take that output, multiply 1 by 3, and I get out of 3. It used to be the case that when I was at 2, I plugged in a 2 and got out of 2. Now it says you plug in a 2, get out of 2, then you multiply it by 3. Well, 3 times 2 is 6. So that just got stretched up. Okay, now it used to be the case that when I was at -2, I plugged it in and got a -3, but now you're taking that output and multiplying it by 3. So it should go down to -9. Okay, that guy didn't move. That -3 right here did not move because he was on the x-axis. This guy, who was also on the x-axis up here at +3, did not move. Stayed right there. Now you'll notice this thing is not the scale at all. I'm claiming that length is 6, but that's even longer than the length of 9. This is supposed to be 2, but that's even longer than 3. None of that matters, right? If you gave me this, I could actually, if I wanted to, I could sit down with a piece of graph paper and get the actual dimensions of the thing. This is good enough for what we're doing. It still goes down, up, and down. It goes through all the correct points. That's why it's important to label the points. That's really all we're trying to do right now. Okay, now let's go ahead and flip it. Because if this is 3, f of x minus 1/2, then we could make, if we make that output negative, if we multiply that whole thing by -1, that's going to flip this thing upside down, right? So let's go ahead and graph that right now. So we're taking all of the outputs from our old one, right? Because that is the output of that right there. Then we're saying just take that number, make it negative, whatever it is. So when the output was 6, it used to be positive 6, now it just drops down to -6. Actually, it might be a little bit better to first do the points that don't move. So this -3 didn't move, the 0 didn't move, the 3 didn't move. So I'm going to go ahead and do those right now. Okay, 3, still here at -3, still here at 0. Those guys did not move. The thing that was up at 6 turned into a negative, so it dropped down to -6. The thing that was at 1/2 was up here at 3. Now it didn't move right or left, so it's still, when the input is 1/2, now it gets dropped down to -3. So there's -3, like that. Okay. This point, it used to be the case that I plug in a -2 and I would get out a -9, but then we just take that, whatever that was, and make it negative. And so a negative is a positive, it flips it up to +9. And so let's do that right there. At -2, we get a +9. And that should be all 6 points that we care about. 1, 2, 3, 4, 5, 6. Now let's connect them. And I can just imagine what happens, right? If I reflected this about the x-axis, then that should be coming down like that, or I'm sorry, it should be coming up like that and then back down. And that's what we're seeing right here. It goes up and then back down. This, instead of going up and down, should go down and then up. That would be the reflection, and that's what we're seeing with these points. Okay, so it goes down and back up. There you go. Okay, and again, I've jacked with the scale. Doesn't matter. We're not doing this on graph paper. It doesn't need to be nice. Every one of those points is marked, and we can be confident that they are correct. The last thing to do, I think I'm going to erase this so that we have some space to do it, is finally, it's a shift. It's a vertical shift by 1 unit. So it's going to be this picture exactly, but just dragged up by 1. So in this case, we don't have to do this, but it'll be easier for me if I just actually use this as a guide. So I'm going to do this and say, okay, all right, let's do these 3 points first. The points that were on the x-axis, if we then take them, take each one of those points and then add 1 to it. We add 1 to the height, then those should jump up to 1. So I'm going to go ahead and say, okay, this is 1. I have a point over here at the same height, and that is at the same height right there. The input value for this one is 3, so I'm going to label that. The input value for this one is -3. Okay. -3 right there. Okay, so I got those 3 points. We just need the other 3 points. It used to be the case that I was at -2, I'd go up to 9, but now we're going to say, well, then just add 1 more to it. So when I'm at -2, I should be up at 10. Something like that, right? Used to be the case that when I was at when I was at +1/2, my output value was 3. Now I'm sorry, -3. We're shifting it up by 1, so it should go to -2 now. Okay, finally, when we were at 2, we got out a -6, but then we took that and we added 1 to it. So if we were at -6, we would be up 1 more at -5. All right, so again, it's the same picture. It starts low, goes up, comes down, goes back up, and it's just been shifted up 1 unit. So we should see the same thing. It should go from down to high and low. And so let's just connect these dots here. Something like that, right there. All right, so, okay. That right there is the answer for this guy. What I'm looking for is that all of these points ended up in the right place, okay? So it should be the case that when you plug in a -3, you get out a +1. It should be the case that when you plug in a -2, you get out a +10. It should be that when you plug in a 0, right, when you're there on the y-axis, your x value is 0, you should get out a +1. You plug in a 1/2, you should get out a -2. When you plug in a 2, you should get a -5. Plug in a 3, you should get a +1. I'm looking also for the shape that this thing, it's like, you know, a roller coaster or mountains and valleys, however you want to think about it. It starts low over here to the left, jumps up to a max right here at -210, comes back through the x-axis up here at 1, right? And then back down for a minimum here at -5 and 2, and then shoots back up and goes through up there. That's what I'm looking for problem 6. The extra credit says to choose the highest and lowest points from your graph g of x in problem 6, and to check your work by plugging in the x value of those 2 points into the given formula for g of x, using the graph of f to obtain the output value and verify that the final output is indeed the y value of your chosen point. Okay, so this is a little, I could not word this very well. I'm sorry, but this is the idea. Okay, so the highest and lowest points. Well, there's 2 of them, right? And on our graph, the highest point here is this one. It is the point, and I'm just going to go ahead and write it down. It's -2, 10. That means the x, when the x value is -2, then the y value or the output value is 10. The lowest point is the point 2, -5, which again is saying when the input value x is 2, then the output value y is -5. Put differently, what your function says, and the thing that we're going to verify is your function says that when x is -2, then the output is equal to 10. In other words, it says that when you plug in a -2 into g, the output you get is equal to +10. This says that when you plug in a 2 into g, a +2 into g, the output you get is a -5. Okay, so that's the information from your graph right there. And what we want to do is verify that with the formula. So let's do that. Let's check the first one. Let's see what happens when I plug in a -2 into this formula. So we want to verify this right here. And we're going to say, okay, well, what is g of, let's just write out g of x first so that it will be even easier to do this. 3 of f x minus 1/2 plus 1. Okay, so that's that. Now let's verify this right here. G of -2. Okay, so when I plug in g of -2 right here, I need to plug in a -2 right there, right? That's like the definition of a function. You say, okay, this symbol goes like this and this and this right here. And so now instead of an x minus 1/2, I have a minus 2 minus 1/2. And at this point, you're going, what do I even do with that? And if we think back to the very beginning of what I was saying, right, it's like, well, what do you do with that? Well, maybe we can make this look a little bit better. I don't know, maybe. Let's just see. Minus 2 minus 1/2. What is that? Well, this is something going into f also, right? And we know what f is. And f has a bunch of different input values here. Funny thing is that all of the input values are in terms of halves. So maybe I'll write this thing, minus 2 minus 1/2 as halves. So what is minus 2 minus 1/2? Well, minus 2 is minus 4/2. So minus 4/2 minus 1/2. Well, that's the same thing as minus 4/2 minus 1/2. That's a total of minus 5/2. All right, so let's just try that. Let's just try to write that way. Okay, so minus 3. F of minus 5/2. Now, if I had a formula for f, I would just plug in minus 5/2. If it were like, to x squared, I would just say, okay, minus 5/2, x, take that and square it. But I don't have that. What I do have is a graph. And I happen to know that the way that the graph is written, that when I plug in a minus 5/2 into f, the output that I get is equal to minus 3. In other words, kind of like originally what we did here is we said, only in terms of f, is that, well, what this graph right here tells me is that when the input is minus 5/2, then the output is equal to minus 3, right? Kind of like, and by analogy, right, that point is minus 5/2 comma 3, but that's what that means. That means the same thing, that when I plug in a minus 5/2, I get out a minus 3, which means that this symbol, f of minus 5/2, is the same thing as minus 3 right here. So I'm just going to replace that symbol. This right here, this f of minus 5/2, that thing, the output of that is equal to minus 3. So I'm just going to replace it. Okay, now I have minus 3 times minus 3. Minus 3 times, well, minus times minus is a positive, and 3 times 3 is 9. 9 plus 1 is, it's 10. And is that what we got? That is what we got. So I verified that that is the right thing. And think about what we just did, right? Like each one of those steps, we basically retraced all of our reasoning to get from this point, to shift it and get it up to this point. We did all of those things before, a minute ago, right? Like when we multiplied by 3, when we stretched it, and then we flipped it upside down. Well, that's ultimately all we did right here. We had a formula for g of x, which told us what to do with an input. And we just went through and took all those inputs and shifted them around a little bit. Okay, so long story short, we verified that our graph, which tells us you plug in a 2, you get out a 10. Well, that is what the formula tells us to do too. When you plug a minus 2 into this formula, you do get out a positive 10. So we have verified that. Let's do it with the other point now. Oh, I just got rid of that. Oh, okay, so g of x is equal to minus 3 times f of x minus a half plus 1. Yep, okay, now we're going to verify the other point. This graph tells me that when I plug in a 2, I get out a minus 5. So let's see what that tells me to do. When I plug in a 2, let's see what happens. G of 2 is minus 3 times f of 2 minus a half. Okay, 2 minus a half. Well, I guess that's 4 halves minus 1 half, or in other words, 3 halves. Okay, so I'll just rewrite it.
Say, okay, minus 3. That's f of 3/2.
And my graph tells me that when I plug in a 3/2, I get out a 2. In other words, it tells me that f of 3/2 is equal to 2. That output right there is equal to 2. So when I see this output right there, I can replace it with 2. So that should be minus 3 times 2 plus 1. Minus 3 times 2 is minus 6 plus 1. Minus 6 plus 1 is a minus 5. And that is indeed what we got in our graph. It says that when you plug in a 2, you get out a minus 5. The formula says when you plug in a 2, you get out a minus 5. And so we're done.